Remember how in Calculus 1 you would try to find the local or relative maximum, local or relative minimum of a function of one variable? You would use the first derivative test or the second derivative test, and if you were really good, you could graph and see where your maximums and minimums in your function were. Remember, local maximum means that in a little area around your point, there is no other point on the graph that is higher. For a local minimum, or relative minimum, in a little circle around the point, there is no point lower. It doesn't mean that far away there can't be higher points than a local maximum, or far away there can't be lower points than a local minimum. But they tell you about the highs and the lows, the peaks and the valleys in the graphs. So you can look back at some of those topographical maps I showed you, the isocline map I showed you, the architecture that I showed you, and see some of those highs and lows. Now in 3D, there is a third thing that can happen besides having a local max or a local min. And I'll get to that eventually. Right now, I want to focus on maxes and mins. Critical values are what you call the places in Calc 1 where a single variable function has a horizontal tangent line or points in its domain where it has a vertical tangent line. When we move into 3D, it's a little more complicated. I need more tangentness going on here. So to have a local maximum, I need to make sure that if I have something like a tangent plane, which we have not discussed, but if I have a tangent plane to that graph, I need to make sure that it is tangent in the y and the x direction, and technically all other directions, so that I don't like sneak up above it whenever I take a little step in any particular direction. And that's really what's going on. You're standing on a point on a surface in 3D, and you take a tiny little step in any direction. If you drop, your height decreases in any direction. Then you have a local maximum. If you're standing at a point in 3 dimensions and you take a step in any direction, if your height increases in all directions, then you have a local minimum. In Calc 1, you had critical numbers, critical values. Now we really have critical points because they're going to be x comma y's, points in the domain of the function. As long as my function has continuous second partials around critical points, then I can do something called the second partials test. Now, where do those critical points come from? Well, it's as I was trying to describe. Places where if I walk in any direction, I either go up all the time or I go down every time. Local maximum, local minimum. Now we get away with just focusing on the x direction and the y direction. The reason why we get away with focusing on just walking in those two directions is beyond the scope of this course. But the way we're going to find the points in the domain where we could have a local maximum or a local minimum. It's going to be very similar to what we did in Calc 1. We're going to look at first derivatives. If the derivative with respect to x is 0, that means that if I walk in the x direction, my height doesn't change with tiny little steps. I have a tangent plane in 3D. Derivative with respect to y being 0 means I have a horizontal tangent plane. We are not going to deal with vertical tangent planes. Yay! So, continuous second partials, first derivatives equal to 0. How do I find out whether I have a local maximum or a local minimum, or maybe neither one? There is this expression here, which is sometimes referred to as the discriminant. And you may have heard that word discriminant used in another context. This is a function of x and y, and you can use a big D to represent it. Take the first or the second partial with respect to x, second partial with respect to y, multiply them. Subtract the square of the mixed partial, and as long as that is positive at your critical points, then you move on to the next step. If your second partial with respect to x is negative, you'll take a look and see that your second partial with y is also going to be negative. The discriminant is going to tell us that by making sure that this whole thing, is positive. So if in either the x or the y direction you're concave down, actually in both the x and the y directions you're concave down, the discriminant tells us that we're concave down in all directions and I have a local maximum. If, on the other hand, the second derivative in all directions is positive, that means I'm concave up in all directions. And I get away with just looking at the partial with respect to x or the partial with respect to y, whichever one you want, because the discriminant is going to suck up all of the different directions that I can walk. Again, the proof of why this works is beyond the scope of this course. It's not straightforward. So here's what we do. Someone says, locate and classify all local extremes of this function of two variables. Take the first derivative with respect to x, partial with respect to x, find the partial with respect to y, set them both equal to 0, and then solve that system of equations. Partial with respect to x equals 0, partial with respect to y equals 0. Find all points in the plane that make those two equations true. And then, second partial with respect to x, second partial with respect to y. Multiply them together. Mixed partial, square it. Plug your critical points into this discriminant. And if that discriminant is positive, then you go down and see, oh, is my second derivative negative? Then I have concave down in all directions because the discriminant's going to make it so by being positive. Concave down in all directions, local max. If the second derivative with respect to x is positive, it's concave up. Technically, this just means concave up in the x direction, but the discriminant sucks up all those infinitely many different directions that we can walk, and as long as that discriminant is positive, I can just look at one direction. I can look at second partial with respect to x or y, and if that is positive, then you know you have a local min. So, what happens when the discriminant is negative. In one direction, I'm concave up, and in the other direction, I'm concave down. Now, I've tried to draw this for you before. Just did a really bad job of it. Remember those hyperbolic paraboloids? One direction concave up, other direction concave down. That point where they come together, concave down in one direction, concave up in another, that point's called a saddle point. It's not a local max, it's not a local min. Go back and look at those beautiful photos of those beautiful buildings that I asked you to look at a long time ago. And you can see that the architect built in some beautiful saddle points in many of her designs. They're still important to know where they are. It's always going to be important to know if there are any and where they are. Just like it's important to know where your highs and your lows are. Now, if it turns out that your discriminant is equal to 0, not positive, not negative, but equal to 0, then just like your second derivative test back in Calc 1, you got no information. Truly, what causes the most difficulty for students in these kinds of exercises using the second partials test for local extremes is in the process of finding the critical points. So I'm going to reiterate this verbally one more time. Find the partial with respect to x. Find the partial with respect to y. Set them both equal to 0 and solve that system of equations, which means you're looking for all points in the domain of the function where the first derivative with respect to x is 0 and the first derivative with respect to y is 0. All points in the plane that satisfy both equations at the same time. Those are your critical points. Then, find your second partial with respect to x, second partial with respect to y, multiply them. Find your mixed partial, either direction, doesn't matter. F sub xx, f sub yy, f sub xy, f sub yx, doesn't matter because all of our functions, those are going to be equal because I'm not giving you pathological functions. And then you create this discriminant. Plug your critical numbers, plug your critical points into the discriminant. If the discriminant is positive, then see if that critical point makes one of your second partials positive. If it does, local minimum. If the discriminant at a critical point is positive, and you look at one of your second partials, not the mixed ones, second with respect to x or y, and you see that it is negative, then you have concave down, concavity in the negative direction in all directions that you could walk, and therefore a local max. If you plug your critical points into your discriminant and you get a negative number, you have a saddle point. If you plug your critical points into the discriminant and you get 0, I got no information to provide you. Other techniques would have to be used, and again, they're beyond the scope of this course.